Hi everyone, I'm going to present learning continuous mesh representation with spherical implicit surface. 3D shape representation is important in computer vision and computer graphics. A common representation of 3D shape is triangulated mesh. Particularly, we're interested in mesh with fixed topology. For example, like human body, human face, hand, feet, and animals. 3D shape representation can enable technology for many applications. For example, can do 3D shape reconstruction from point clouds or reconstruction from single image, and can be used in CG actors and also like consumer application of Animoji, etc. However, mesh is discrete representation of 3D shape, and in the real world, 3D shapes are continuous. In this paper, our goal is to represent mesh in a continuous manner so that we can process a 3D shape in aperture resolution as needed. First of all, I would like to introduce spherical conformal parameterization. Given any closed manifold G0, we are able to map each vertices to a sphere so that we can create a one-to-one correspondence from the mesh to the sphere. Inspired by this kind of technique, we can always map a mesh to the spherical coordinates. If the mesh is not a G0 meshes, we can always split the mesh into several closed manifold G0 meshes. For an individual mesh, we can map the mesh into the spherical coordinates theta and phi, and then we train an MLP model to map each spherical coordinates to the vertices xyz. After the MLP model is trained, we can sample the spherical coordinate continuously to get the continuous spherical coordinates, and then we can reconstruct the mesh surface continuously. We can also train our SSI representation for a class of mesh, for example, face with different identity and expressions. Given any face, we can always encode the mesh with the global features and concatenate it to the spherical coordinates to decode the mesh so that we can reconstruct mesh with different identity and representation. Our SIS representation can also be conditioned with local features to have a higher representation power, especially for application of super resolution. Here is the pipeline. Given a mesh, we can subsample some point cloud and then map the point clouds to a sphere to construct a low resolution mesh. For each vertices, we concatenate with the 2D spherical coordinates and then using MLP to map each vertices to a local feature Z. And based on barycentric coordinates, we can fuse each triangular face features to any of the vertex point, and then feed the fused local features with the 2D spherical coordinate, and then finally to predict the to any surface points vertices xyz. To evaluate our method, we use two datasets, DFAUST, which is a human body dataset that collects over 40,000 real meshes, and COMMA is a human facial dataset which consists of 12 classes of extreme expressions. We use add-in optimizer. The batch size is set to 64 and the total epoch number is 200. We evaluate our method with two tasks. One is reconstruction and the other is super resolution. For the reconstruction task, we compare our method with LSA, FitSTNet, and TTFOAM. Here, the X mark means those methods cannot support for any resolution reconstruction. So compare TTFOAM, our method can perform better in both datasets. And for the comma dataset, our method is even better than FitSTNet. For the super resolution task, we compare our method with barycentric coordinates interpolation. So in both datasets, DFAUST and comma, our method consistently perform better than the barycentric interpolation. And here are some qualitative comparison. We can see that our method produce better visual results. Here we're adding ablation study for the SIS representation with local features. We can see that after adding the feature fusion module, the method is perform better in both DFS, AU, ST, and comma dataset. Here's the conclusion. We learn a continuous representation for mesh using our devised spherical implicit surface. Our SS representation builds a bridge between the discrete and continuous representation in mesh and can naturally exploit the information provided in different resolutions. At last, we show that this continuous representation technique can be effectively applied for downstream tasks like reconstruction and super resolution of 3D shapes. Thank you very much.